Okay, good morning, everyone. Let me first quickly go over the results for the quiz. We have a lot to do today. So I'll give you the answers, and then we'll go on, and we're going to be looking at chapter 11, our last chapter. Okay, so again, these will be in a different order, and the answers may be different order from yours, but these are the questions. So this was choose more than one right answer. So everything that will lead to zone broadening. So remember, large particles. Remember, we want those to be small. Small column diameters, that's good. Thin films, that's good. But large H, that's bad. Okay, so this would be these two were the correct answers. This one is a simple definition. How long does it take a species to move through the column compared to the unretained? That's the retention factor. If you want to improve resolution, which of these should you decrease? Okay, remember N, we always want that to be large. Selectivity, we want to be large. So flow rate. If you slow down the flow rate, it will take things longer to go through the column. That will improve your resolution. It will also cause zone broadening to increase. Okay, how do you solve the general elution problem in liquid chromatography? So remember, that's gradient elution, which means that we change the mobile phase during the run. Okay, if I ask the same question for gas chromatography, then that would be temperature programming. Okay, so that was the first four. Then two short answers. So what was an optimal, the best range from K? That's 2 to 5. So a few of you had 2 to 10. 2 to 10 is considered good, but 2 to 5 is best, optimal. What do you want in terms of resolution and retention time? Okay, so for these two factors, what do we want for a good separation? So remember, I repeated that over and over. We want a good resolution, which means at least 1.5 and a short retention time. Okay, and then the bulk of the quiz this time was calculations. So they first asked for retention factor for A and B. So here's the formula, and you should have had these two numbers. By the way, pay attention to my significant figures. Most of the time, I did not take off points unless you were really crazy with your significant figures, but you do need to pay attention to those. Okay, B, selectivity factor, that's alpha. So 3 ways you can calculate it. Since you already have these two numbers, that's the easiest. Remember, alpha, always bigger than 1. So it's always the bigger one divided by the smaller one. So in this case, that's 1.11. C was calculation of the average plate height. So you have to calculate them for A and for B. Turns out they're the same if you're doing the right number of significant figures, which notice is only going to be 2. So your answer should have been 1.9 times 10 to the third. D was resolution. So that's this equation right here. And notice here, 3 significant figures. These have 2, but when we add them, we're going to have 3 because that's the addition rule. So you actually should have 3 for this resolution number. So that should be 0.924. Okay, now, is that a good resolution? No. We just saw resolution needs to be at least 1.5. Okay, so the next question said, what length of column do you need to improve the resolution? There are 2 ways to do this. Okay, by far, the easiest way is to use this one. Okay, it comes from this big equation, but you should use this form where R1 over R2 is equal to the square root of L1 over L2. Okay, then it's just this simple equation. You solve for L2 and you get either 105 centimeters or 1.05 meters. If you want to go through N, a lot of you did this the long way, then you have to calculate the new N, and then you have to calculate H, and you will get the same answer. Significant figures is different. Okay, but again, I highly recommend that you just go through L. It's easier, it's simpler, there's less math. Okay. F then asked, what's the time on this new column? So that, again, that comes from this great big equation, but it simplifies to this little equation. So you put in the numbers and you get 23.6 minutes. Most people did that correctly. Okay, and then finally G asked, is this the best way to improve the resolution? And the answer is no. Notice this retention time is getting much longer. We had 9 minutes, now we have almost 24. So the retention time is getting long. And if you get a longer column, you have to buy a new column, which costs money. Now, I also told you in class, usually when we make a longer column, that means the column is getting too long. For this particular problem, this actually 1.1 meter is not too long for a GC column. Remember, packed columns are usually 2 to 3 meters. So a better way, I did not ask you this, so all of this, note, this is extra information. It's best to try to change temperature before you go buy a new column to get a better resolution. Okay, so that was quiz 4. A lot of you did pretty well, some of you not so well. All right, today we are going to, stress again, I've been talking about these all year, but these are ways to lose points on the calculations. So of course, if you do it wrong, if you do the math wrong, if you don't show your work, most of you did that. If you don't pay attention to significant figures, if you don't give units, if you don't give me your name and student number on the paper. And I didn't take off points for this, but you should do this so that I clearly know what your answer is. Okay, so these are things you always need to be aware of for calculations. Okay, now we are ready to move on to our last chapter, chapter 11, which is the liquid chromatography portion. So this technique is called high performance liquid chromatography. A lot of people see this abbreviation HPLC and they think the P stands for pressure because this method is done under high pressures. But the P is not pressure, it's performance. So this method is actually the most widely used separation technique. It is more common than GC, and that's because you can use it for more materials. Remember, for GC, we have to get my analyte into the gas phase. In LC, we don't. And there's lots of things that don't easily go into the gas. So this works good for non-volatile species. It's a sensitive and accurate and precise method, and it's used in all kinds of areas to separate materials. So there are several different kinds. By far, the most common is this one that we call partition. Okay, all of these are liquid chromatography. And there's actually 2 kinds of partition, and we will spend most of our time today talking about this. We will then briefly talk about these 4 other kinds. And this picture kind of shows you quickly what are some of the differences. So the partition that we'll be talking about, your stationary phase actually has the liquid stationary phase on a support. So the stationary phase is actually a liquid on a solid. And then your analyte goes into and out of it. This is where we have that partitioning, that equilibrium we've talked about for the separation. In absorption, you have a solid stationary phase and the particles just interact at the surface. Okay, there's not that partitioning. Then we have one where we actually are going to separate ions. Things get separated based on being a plus ion, cation, or a minus ion, an anion. There's another one, size exclusion, or here it says molecular. This is where we separate based on size. And then there's a newer kind called affinity. This is a kind of chromatography that separates one very specific molecule. It's usually used for biological molecules. Okay, but we'll talk about all of these in more detail. Okay, now what kind are you going to use will depend on several factors. It depends on the molecular weight, the solubility. Does your sample dissolve in water or in hexane or in what solvents? That's related to polarity. And then is your analyte ionic or non-ionic? So this chart, notice it shows you the molecular weight up here and the different solvents. It gives you an idea of where you might use these different kinds of chromatography. Okay, so let's start off by just reviewing quickly. Remember in chapter 9, we said for a good separation, we want, it's on the quiz, good resolution and a short time. Okay, now, two of the things that we can try to adjust to help resolution in time are N and H. And remember, we want N to be big and H to be small. And we talked about that these are controlled by zone broadening. Okay, and we talked about these different variables that affect the zone broadening. There is one other factor that can affect H and N, and that's the sample size. Now, this is not true for all columns, but for many columns, as you increase the sample size, the plate height increases. Okay, remember plate height is H. So more sample, H gets bigger, which remember is bad. We want H to be small. So what that means is quite often when we're doing these separations, we want a small sample size. So usually we're talking 10 to 50 microliters. We already know that we want small particles on that stationary phase. And we also want the tubes that are carrying things to the column and to the detector. We want those to be small so that we don't get a lot of broadening outside of the column. So everything we want is small, small, small. Okay, so the instruments, we said, okay, we want these small particles. And notice typical particles are 2 to 10 micrometers. Now, remember, last week in GC, we said, oh, usually these particles were about 200, 300, up to 500 micrometers. So GC particles are much bigger than HPLC particles. So because these particles are so small, that means we're going to need a high pressure to push things through the column. And what that means is that we're going to have, pressures of around 1,000 to 5,000 psi. So that means the LC instrument is more complicated and more expensive in GC. If you're currently in China, you've had the lab, and the experiment you did for chromatography was GC, okay, because GC is a cheaper method than HPLC. So the instrument is more expensive. In addition, the mobile phases are more expensive than the gases. These mobile phases have to be solvents that are very pure. They're actually the purest solvents you can buy, so they're expensive. And they can have no dissolved gases in them. Okay, so that adds to the expense of this method. Okay, so let's look at the instrumentation. So here's a diagram showing a basic setup. And notice here, this is where we're going to have our solvents. And then we'll need a pump. And then we've got a whole bunch of stuff. But all of this basically is to get the sample into the injector valve and then bring it to the column and then off to a detector. Okay, so the first thing that we see is we have these different solvent reservoirs. Okay, and I already said that this solvent has to be free of particles and gas bubbles. Okay, the particles can clog up the column, the gas bubbles can get trapped in the detector. So usually we keep these in reservoirs. They're often just glass bottles that we store these in. But one thing we always have to do before an experiment is we have to get rid of any gases and any particles that are in those solvents. So there's 3 ways to do that. This process is called degas. So the most common is to use a vacuum or suction filter. So this is just a filter that looks like this. And right here is a small pore filter. And you pour your solvent through here. You have a stir bar here, and you have a vacuum here. And that will remove all of the gases. You can also do this same method using ultrasonic. Again, putting a vacuum on your solvent. Or a third way is to use a helium purge. This is called sparging, which means I'm going to bubble helium through my solution, and the helium will force out the other gases that are there. And if you look at this system, notice it talks about a sparging unit, and it talks about a helium source. So this would be an expensive instrument that is actually using helium to do this. Again, the most common is to use this kind of setup. So you go in first thing in the morning, you degas your solvent, and then you pour it into these bottles. And then you can usually go, depends on the solvent, but often you just do that once a day or maybe twice a day to remove the gases. Okay, so that's the solvent system. Now, notice that we have the ability to use different solvents at the same time. There's a valve that's going to be mixing these solvents. And when we do a separation, we can do 2 kinds. Okay, one is what we call isocratic, and the other one is gradient. So we've already seen the word gradient. So anytime you see iso, that means the same. So isocratic means one solvent system. And now it's not one solvent, it's one solvent system. So for instance, maybe I'm using 20% methanol and 80% water. Okay, that's one system, and I use that same system through the whole experiment. Isocratic is when you change it. You start at 20-80, and then you slowly change it to 80-20 at the end. So you're changing it during the experiment. And we've talked about that this often gives you a much better separation. And you can use 2 or 3 solvents to do this. So the next couple of slides just show you the power of gradient elution. So notice isocratic took me over 25 minutes to get out 10 peaks, and these early peaks, a lot of these, the resolution is not that great. Then they did gradient, changed the solvent, and notice now I get all 10 peaks out less than 15 minutes and pretty good resolution for a lot of them. Not perfect, but better. So this overall is a much better separation than this, using that gradient elution. Okay, so that's the solvent system. Now, as I said, we need a pump to get it into the column. So these pumps have to give you pressures up to 6,000 psi, and we want a constant flow rate. We don't want a pulse where the flow is high and then low and high and then low. Typical flow rates about 0.1 to 10 milliliters per minute. And we want the flow rate to be reproducible. The pump has to not corrode from the solvents. We are putting these solvents under high pressure, but there is not a risk of explosion. Solvents might be flammable, but they're not going to explode because they're actually not compressed. Okay, so for the pump, over 90% of the systems all use this thing called a reciprocating pump. So you can see there's a small chamber here with a piston, and basically it sucks in solvent, and then it pushes it out. That's how a reciprocating pump works. And notice it can go up to the pressures that we need, even higher. But the one problem is that this does give you a pulse, because it's sucking in and pushing out, and then sucking in and then pushing out. So you get a varying flow rate. So as part of the system, you'll have something called a pulse damper. What this does is smooth out the flow rate. Okay, so that's the reciprocating pump that is located here. Notice all of these other things in the diagram. There's a priming syringe. Often when you start the pump, you actually have to suck out all the air and you use a syringe, so that's called priming. And then you have some filters to, again, make sure that there's no particles in that solvent that's going to get into your column. And then some pressure regulators. In the more expensive systems, this would all be controlled by a computer. Okay, so that's the pump. Next, the injector valve. So remember, the injector's valve is to get the sample onto the column. And the way we do that most of the time is to use this injection loop that I talked about last time. So remember, we have a small loop. You can change the volume. And first thing you do is fill up that loop with your sample. And then you turn a dial, and then that solvent, the mobile phase, will wash out that loop and send that off to the column. Okay, the columns are usually made of stainless steel. You can see a picture of some columns here. And remember, we talked about one way to improve N is to get a longer column. But then you have to buy a new column. So this is what columns can run, $200 to $1,000 US. And renminbi multiplied by 6 to 7 right now. Okay, so it's a pretty good expense to buy a new column. So columns can have lengths of usually 10 to 30 centimeters. The most common is 25 centimeters. Now compare that to the GC. Remember, the GC packed columns are 2 to 3 meters. So LC columns much, much shorter. Inner diameters a little bit bigger. And then, of course, the packing sizes, as I already mentioned, the particles are much, much smaller than GC. And that's why we need this pressure. So this gives you kind of the most common columns, but again, the length, the packing size, the diameters can change. Typically, ends are about 40 to 60,000 for these kinds of columns. Okay, and we'll come back and look at the stationary phase inside the column in a little bit. So that's the columns. Now, one thing that we almost always will use for chromatography is something called a guard column. So this is a small little column that goes in front of the regular column. So right here, this would be that regular column to do the separation. Okay, so then you have this little column, it's usually a couple centimeters big, that's called the guard column. Now, what does a guard do? Okay, a guard is there to protect things, right? So this column's job is to protect this main column. Remember this expensive column, right? Well, what is it protecting it from? Well, one thing is sometimes there's something in your sample that will bind on your column and will not come off, okay, irreversibly. So instead, we have that thing bind to the guard column and not your good, expensive analytical column. Another thing is sometimes some of the stationary phase will come off the column and go into the mobile phase. So if that happens, we're going to let that happen in the guard column, again, to protect this one. So these guard columns are much cheaper to replace than the regular column. And in fact, often you can pack them yourself. So here's a picture of a guard column. So usually what you would do is you would take out this one end, this end is sealed, and you can actually buy a bottle of stationary phase. And then you take that guard column and you pour in a little bit of stationary phase, and then you tap it, tap, tap, to get it kind of packed down, and then pour in a little bit more, tap, tap, to get it packed down until you get it full, and then put on the other end. Now, the packing's not as good as the ones you buy, but it's okay for this little short column. And then when you need to replace it, you just clean it out and repack it. Okay, so very important piece of a separation. Now, I mentioned these column packings. So there are two kinds of column packings. Usually for the guard column that I just talked about, we just have these beads that are made of silicon dioxide, and then we put a film of stationary phase. Notice 30 to 40, no, that's not the film, that's the size of the bead. So notice these are much bigger particles, and with this thin film of stationary phase. And this is more commonly, again, just for guard columns. Now, what about that regular analytical column? What's inside that? Well, those are usually these porous beads, which are much smaller. Notice 3 to 10 instead of 30 to 40. And they also have these small, thin films of stationary phase on them. Usually they are chemically bonded onto those beads, again, so that they don't bleed off. Remember bleed? When the stationary phase comes off the column, we call that bleeding. So this picture, they're probably not going to be strange shapes like this. They're probably all going to be the same size, the same shape, and then we'll have the film on them so we can pack them nice and tight into that column, because we don't actually want holes in there to get a good separation. Okay, so that's the column packings. Now, what about detectors? So for the detector, we need everything that we said we want for GC, except we do not need the temperature range. LC is almost always just done at room temperature, one temperature. We do want the volume of the detector to be small so that we don't get broadening inside the detector. So HPLC detectors, there's two types. There's what's called bulk property, and bulk property detectors will respond to everything. But the response from the mobile phase and the analyte will be a little bit different. And the most common bulk detector is what we call refractive index. So we'll look at that. More common is a solute property detector. These respond only to the solute. So your mobile phase gives it a low signal or zero signal, and then when your solute comes, you get a signal. And some common ones would be UV vis absorbance, IR absorbance, electrochemical, okay, and we'll look at a couple of those. So this table shows you some of the common detectors for HPLC. By far, the most common is UV absorbance. Now, there is one kind of correction to your notes. Most of your notes say UV vis. And really, it's usually just UV. They don't use visible light. They use UV because almost everything will absorb in the UV. So it's really better to say UV absorbance. Okay, so the UV absorbance, there's lots of different kinds of detectors. You have to think now back to chapter 4. So some of the detectors will be filter-based. So they'll use a mercury light, which remembers a line source, and it has a very strong line at 254, which is a great place that most things will absorb at. So this is the most common line, and then you have a filter for that. You can also use a variable wavelength. So you would use a continuum source. Okay, remember the deuterium lamp, and then a monochromator. So remember what the monochromator does? It selects one wavelength. So if you have this kind, it's more useful because now I can select any wavelength in the UV range. There are also a few instruments that are more expensive but use a PDA. So you're going to have a continuum source, probably a deuterium lamp. And remember, the PDA, we can measure the whole spectrum at one time. So this is a more powerful detector, but also more expensive and less sensitive than this one would be. Okay, so the setup, no matter which kind you have, here comes your stuff from the column, and then you have your UV source shining through here, and then the detector, whether it's a PMT or the PDA out here, to detect when you get absorption. And if you need to scan the whole spectrum, like for PDA, you would actually just stop the flow for just a second so that you can pick that spectrum. You could also use this setup with IR light. We didn't talk about IR, but I'll just tell you IR is not as useful because most organic solvents absorb IR, which means your mobile phase absorbs. Okay, and the idea for this detector is the mobile phase would not absorb, but the solute, the analyte, would. So this is a solute property detector. All right, so here's an example of what your chromatogram might look like. So notice I have 3 things that I'm measuring. And notice we measured at 240 nanometers. Now, notice something interesting here. Notice that these 2 concentrations are the same, but their areas are not the same. Why not? Remember, for absorbance, what is the equation that governs how absorbance and concentration are related? Okay, well, remember Beer's law, which tells us absorbance is proportional to concentration. Okay, but these are the same, these are not. Why not? Okay, well, remember this guy right here. Remember molar absorptivity or absorptivity. And remember that is a constant for a molecule, a given molecule at a given wavelength. So if you change the molecule, this number changes. You change the wavelength, this number changes. So when we look at these 3 compounds, they actually all have different absorbances at, they're looking at 240. So notice the absorbance is not the same for these compounds. So that molar absorptivity is different for each of those. So what that means is you actually have to do a calibration for each analyte. So if you have 3 analytes, like here, you have to do 3 calibration curves, okay, because they each respond differently to the detector. All right, this just kind of shows you the same thing. So again, I'm measuring these same samples, and they tell you their absorption maximums here. And notice when I change the wavelength that I measure at, then I'm changing the areas. That's because absorptivity is changing. Okay, we also said you could use the PDA. This is what that setup would look like. So the stuff comes off of the column, and then the light will go through it. So this is coming off the column right here. The light goes through it, and now remember we're measuring the whole spectrum at one time. It only takes a second. So we stop it. Notice they stop it every 5 seconds, and they take a scan. And notice the background, 0, 0, not responding to the mobile phase. But then once these compounds start coming out, then we see peaks of response. Okay, so that's UV detection. Another detector is a refractive index. So this is what the setup looks like. You actually have your sample on one side and then a reference solvent on the other. And then you have light going through it. And if the solution is different, then the light will bend and you will get a different number. So it will detect your sample as it passes through. Now, this detector will respond to everything. So this is a bulk property detector, okay? And that's one good thing about this is it responds to everything. So it's almost a universal detector, which is, of course, what we always want, to respond to everything. However, this detector is not very sensitive, and which means we cannot measure very low concentrations. And it's also very sensitive to temperature. So if you have even a small temperature change, that will affect your results. All right, one other kind of detector we'll look at are electrochemistry. Now, we have talked about some of these. So notice one way would be to measure potential. We talked about coulometry, where we apply a potential and then measure I, or integrate I. One of the most common detectors uses what we call amphiometric. This is where we have a fixed potential and then we measure current. And we can use either 2 or 3 electrodes, depending if we need to maintain that potential or not. And almost everything will respond. If we look at this chart, we see that pretty much all kinds of compounds can be oxidized or reduced somewhere. Okay, so the cell would look like this. Again, here comes my stuff from a column. My working electrode is here, so I apply a potential. So my stuff from the column comes, it gets oxidized or reduced. The reference electrode and counter electrode are downstream, but then we measure that current, we get a signal. And again, this will not respond to your solvent, but will to your analyte. So this is solute property. Okay, there are lots of other detectors, but those 3 are among the most common. Notice absorbance, the limit of detection, we can measure picograms, that's 10 to the minus 12. Usually electrochemical are 100 picograms, so still pretty good. And notice they both have pretty good dynamic ranges. The refractive index, notice it can only measure nanogram, 10 to the minus 9. And the dynamic range is smaller. So remember we said refractive index is a little bit less sensitive. Okay. But again, most common UV absorbance. Oh, there's one place I didn't get that changed. Okay, so UV absorbance. Okay, so that's the instrument. And pretty much all of these will have those different parts. So now we want to start to look at these different types. And again, we'll start with partition, which again is the most commonly used and the most important. And it has 2 types, what we'll call normal and reverse phase. So this partition is good for low molecular weight analytes, okay, fairly small molecules that have molecular weights less than 3,000. It can be polar or nonpolar. It works for both. Usually the stationary phase will be a liquid that is on a solid support. So again, we'll have these small particles, and then the stationary phase will be a liquid that's bonded, chemically bonded onto that particle. And as I said, there's 2 kinds, normal and reverse. Okay, so in both of these, that stationary phase are going to start out with these same materials that we saw for GC. Okay, so this guy's a silanol, and then we do some chemistry on it and get this siloxane. And we can change that R group to give us different kinds of columns. So we have this silica support, SiO2, and then there'll be different chain lengths on it for different types of stationary phases. So the first, remember, was normal phase. So in normal phase, your stationary phase is polar, and your mobile phase is nonpolar. So typical stationary phases might be that silica surface that's not modified. Notice all these OH groups. This would be a very polar stationary phase. We can also use these siloxanes where this R group would be something like CN or a diol or NH2. All of these are polar. Okay, so stationary phase is polar, and the mobile phase is nonpolar. So the mobile phase will be something like hexane, okay, ethyl ether. And that's the O with a CH2, C2 group and a C2. That's ethyl ether. Chloroform, CHCl3. Okay, so polar column, nonpolar, mobile phase. That's what we call normal phase chromatography. Okay, the other kind is called reverse, and it's just the reverse of this. So here now, the column will be nonpolar, and the mobile phase will be polar. So here, these R groups will usually be carbon chains, like C8, which is called octal, C12, dodecyl, C18, octadecyl. C8 and C18 are the most common. So non-polar carbon groups will be these chains. And then the mobile phase, polar. So usually it's water with some other solvent that's miscible. And miscible means that it's easy to mix with the water. So something like acetonitrile, methanol, ethanol. Okay, now today, almost 75% of chromatography is reversed phase. Okay, so reversed phase is more common than normal phase. Okay, now that sounds kind of strange. You know, if I say something's normal, we think, oh, that's most common, most typical. Okay, but I just said reverse phase is more common. Okay, well, why is the other one normal? It's normal because it came first. The very first columns were these very polar columns. So this came first and they called it normal. Then later they found actually this reversed phase, these non-polar columns, are actually more useful for more separations. Okay, so reversed is more common, but normal came first. Okay, now let's look at how we would separate things on these two different columns. Okay, compare normal and reverse. So I made this little chart for you. So notice that I have told you that, okay, the stationary phase in normal, polar, and in reverse, nonpolar. Mobile phase in normal is nonpolar, and in reverse, polar. Okay, now I'm going to do a separation with the same three compounds, one on normal phase, one on reverse phase. And notice I have three analytes. And A is the most polar, and then B and C is the least polar. Okay, so on the normal phase, normal, remember, stationary phase is polar. And remember, if I have a polar compound on a polar stationary phase, then that compound will stay longer than nonpolar. Remember, like dissolves like. So the polar compound likes the stationary phase more than the nonpolar. So when they come out, what comes out first? Okay, the nonpolar, and then last will be the most polar compound. And now notice for reverse, it's exactly the opposite. Here, the stationary phase is nonpolar. Okay, so who's going to come out last? The nonpolar compound, because it likes the nonpolar stationary phase. And then first is the polar. So notice the two orders exactly reversed for that. Okay, I can also, now I can't change that order, but I can change the time by changing the mobile phase. So notice here, the mobile phase had a low polarity. So if I make the mobile phase more polar, that means this polar guy is going to want to be in this mobile phase more than before, so it's going to come out a little bit sooner. Okay, and then the same thing over here. Here I've made the mobile phase less polar, so the nonpolar guy will come out a little bit sooner. So by changing the mobile phase, I can adjust those times for when things come out. Okay, so that then brings us to, before we get to that, let's look quickly at the effect of the chain length in reverse phase. So remember, reverse phase, stationary phase is non-polar. So this is where the stationary phase are those carbon chains. So notice we have three columns. Here the carbon chain is just methyl, one carbon. Here octal, 8 carbons. Here octadecyl, 18. And notice the retention times for these. Okay, notice that with the methyl, they're out in 8 minutes. With the C8, takes 16 minutes, and with C18, 24 minutes. Okay, now why the difference? Well, remember, in methyl, we got these little tiny chains versus the octadecyl. We have these very long chains. So here the analyte will come in and interact, and then it comes back out, but it's just a short time in those chains. But here, the analyte can go down and then back out, so it will interact for longer. So you get longer retention times. So in general, the retention time will become longer if you have longer chains. You can also put more sample on longer chains. Okay? The longer chains can accommodate a bigger sample size than the smaller chains. Okay, let's go ahead and take a break there. And then after the break, we'll look at the method development for this kind of chromatography. Okay, the method development for HPLC is much more difficult than GC. So remember, in GC, the mobile phase just carries the sample. It just transports it. In HPLC, the mobile phase interacts with the solute. So you have to always balance the interaction between the mobile phase and the stationary phase. So it's much more complicated. A lot of the development depends on the polarity of the things that you're dealing with, of the polarity of the mobile phase, the polarity of your analytes. So in general, if you look at polarities, we have hydrocarbons down here. Those are the least polar. And then, of course, water is the most polar. And you can see the order here, above hydrocarbons, then we have ethers, and then esters, ketones, aldehydes, amines, alcohols. Those are the general orders of polarities. And usually you try to choose your column so that the polarity of the column matches your analyte. If you match the polarity of the mobile phase with the analyte, then the analyte likes the mobile phase and it will just stay there. It won't interact and you won't get a separation. So you try to match the stationary phase polarity with the column. But ultimately, you just have to use trial and error. If you've got a new system, you're trying to develop a separation, you have to just keep trying different solvents, different columns to get the best separation. All right, so we've talked about things that affect a separation are N, which we want to be big, and then the retention factor and alpha are measures of separations. We said we want the retention factor to be 2 to 5. That's the best. And alpha, bigger means better separation. So to change N, we've talked about to change N, we can change L, but that means buying a new column, and that's expensive. So often we focus on trying to change retention factor. And the retention factor is very related to solvent composition. Okay, if you change a solvent composition, meaning if you change the ratio of a solvent, you will greatly affect your separation simply by changing the polarity of that mobile phase. So remember we said the best, K is best if it's 2 to 5, and we said 2 to 10 is good, but in the real world, we don't always get what's best. So what actually works in the real world is that retention factor has to be between 0.5 and 20. Okay? So if that retention factor is between 0.5 and 20, it works. All right, and so we said we can change the retention factor by changing solvent composition. We can also try to change alpha, the selectivity. And we do this by changing the mobile phase or changing the column material. Okay, but remember, if we change the column material, that means buy a new column. All right, now this kind of sounds the same. Both of these were saying change the solvent. Okay, but the difference is to change retention, we use the same solvent system. So like if we're using that water methanol, we just try different ratios of water and methanol. to change selectivity, we actually try a different solvent. We use water and something else. Okay, so that's the difference between these two. All right, so here's a couple of examples. So notice here they did this separation with water and acetonitrile, and very poor resolution. Everything came out fast, but resolutions are terrible. And for this system, K is 5. So then they changed it, 3070. And notice it's a better separation. It's still not good. We still don't have resolution of all the peaks. But notice simply by changing the ratio, we've changed K from 5 to 10. And there are actually equations you can use to calculate how this will change K. The equations are a little bit hard to use, so I'm not giving them to you or asking you to learn to use those, but there are equations to help calculate how changing this ratio will affect K. All right, so we said if we can't get the retention factor we change K and we still don't get a good separation, then we try to change selectivity factor. So here we're going to use different solvents, but we're going to try to still keep K, the retention factor, about the same. So if you're using reverse phase, usually you'll use methanol or acetonitrile or tetrahydrofuran. That's a 5-membered ring with oxygen in it. So use that to adjust the strength with water. For normal phase, we'll use ethyl ether, methylene chloride, or chloroform to adjust the strength of N-hexane. So here's an example of that. So remember we were using up here water and acetonitrile, and we didn't get good. So they changed to water and methanol. Okay, still 10, and notice now this is quite nice, this not so good. So they changed to water and THF, and now not so great. Here they tried 3, water, THF, and acetonitrile, and this is better, but this is still not great. So that's why it's trial and error. You just have to keep trying them till you find a solvent system that works. And sometimes you might have to do the gradient elution, get a system that works pretty good for these 3 and then change it to get these 3 or something like that. Okay, so that's partition chromatography. Again, this is the most commonly used, lots of different places it's used. This table just shows you a few of the areas and a few of the kinds of mixtures that you can separate. Okay, we now want to look at these other 4 kinds of chromatography. We're going to look at these much faster and just try to understand the big picture of what these do. All right, so the next one is absorption. This was actually the first kind of liquid chromatography. So this is where the stationary phase is a solid, and then the mobile phase is a liquid. So the early stationary phases were actually that bare silica or else the sky alumina. And notice that these are very polar, and we use this to separate non-polar compounds that have molecular weights less than 5,000. Now, that might seem like a contradiction because remember, I said, we try to match the polarity of the analyte with the polarity of the stationary phase. And notice we're using non-polar analytes and polar stationary phases. Okay, now why? Well, polar compounds love these stationary phases, and they love them so much that they will not come off of them. They get on there and they stay there, sometimes forever. So they don't work well for polar compounds. Again, if you need to change the retention factor, you change the mobile phase. You can't do anything with the stationary phase for this. I'll just point out quickly a difference between these 2 words. We've talked about absorption when we talked about absorption of light. So absorption means something goes into something, it penetrates. Adsorption is what we are talking about here, and this is only on the surface. Okay, so these molecules are not going into the solid, they are only on the surface. Okay? Surface interaction, and then they come off. That's the separation. So this is the least popular type of chromatography. Part of the problem is those stationary phases change over time as they become exposed to water or pH. It ruins the stationary phases. Okay, so as I already said, non-polar compounds, molecular weights less than 5,000. There's some overlap. There are some things that you can do with adsorption that you can also do with partition, but usually they're complementary. Okay, what does that mean? Well, it means if partition can't do it, then sometimes absorption can. And what partition can do, absorption cannot. So they work well together. One thing that adsorption can do that's quite important is it can separate isomers. Okay, these are compounds that chemically have the same structure, but there's a difference in rotation. And these are very hard separations to do. So one way that you can sometimes do this is using adsorption chromatography. Okay, so that's it for that. Next one we want to look at is ion chromatography, or it's also called ion exchange. So they first actually developed this way back in the 1940s, but it took them 30 years to figure out how to handle the detection. So as you would guess from the name, here we are going to separate ions. So this is based on an equilibrium between a stationary phase and ions in solution. So most of the stationary phase have this kind of structure. This is polystyrene cross-linked with benzene. And then they have functional groups. So notice these, if you want to separate cations, you have either the SO3 or the COO minus, and there's a hydrogen ion. If you want to separate anions, then instead of these, you would have NH3OH or this OH. Okay? And then you're going to separate anions. So the way it would work with a cation, here's your stationary phase, and this is what you're trying to separate. So what happens is this actually goes onto the column. It changes places with the hydrogen, and the hydrogen comes off. Okay. Anion, same idea, except now the anion goes on to the column, and the OH comes off of the column. Okay, and you get these equilibriums. So looking at the equilibrium, this is the process. So we have the stationary phase, and then the cation in solution. And then there's an equilibrium with that cation going onto the column and this hydrogen ion coming off. And we could actually write an equilibrium expression for this. So the way this works is we would take my analyte ions and I would get them stuck onto the column. Okay, and then off comes the hydrogen ion. Now, how do I get them back off the column? Well, notice this is an equilibrium. So if I change the hydrogen ion concentration, if I increase this concentration, I'm going to push this equilibrium back this way, which means that ion that's on the column is now going to come off. All right, so that's how it would work with a single cation, but we actually want to separate, say, several cations. And the reason this works is because different ions have different affinities for the column. Okay, now what that means is some ions like the column more than other ions. So notice that thallium really likes the column, whereas lithium not so much. Okay, so what it means is as I start increasing hydrogen ion, first guy comes off as lithium, then hydrogen. Sodium will come off next, and very last would be thallium. And here's the order for +2 ions, and also the order for anions. So the ones on this side, they come off last because they like the column more, and the ones over on this side, they will come out first. Okay, so the process, I've got my column, and in the beginning, I've got all these hydrogen ions, okay? All these hydrogen ions filled up with my column. Okay, now I'm going to take my solution. And let's say my solution has potassium and sodium and rubidium in it. Okay, so I'm going to wash it through the column. So what happens is all of those, the rubidium, the potassium, the sodium, they all get stuck on the column. Okay, and out comes the hydrogen ions. So now all three are on the column. I want them back now. Okay, so I start increasing the hydrogen ion. Okay, and so the first one that comes off is sodium. So out here I got my detector. I'm going to get a peak. That's sodium. Next one that come off, potassium. And then finally, rubidium. Okay, as I increase hydrogen, and I'll get a nice separation of those ions. The divalent cations always have a bigger affinity than the monovalent. So these will come out later than single charges. So here's a couple of separations, just using simple cations and anions. And notice those single cations came off first, and then we have magnesium, calcium, strontium. If we go back here, notice magnesium's not there, but here's calcium, then strontium. Oh, there's magnesium. Okay, so they come off in that affinity order. Same thing over here for the anions. Now, we can separate either cations or either anions, but we cannot do both at the same time. Okay, cation, you need a cation exchange column. Anion, you need an anion exchange. And notice the mobile phase is usually water, and then we use carbonate or hydrogen carbonate to control the pH. All right, now what about the detection? I said that this was actually a big problem. An obvious detector is conductivity. Okay, conductivity is a simple detector. It's universal. It will respond to all ions. It's cheap. It doesn't break. So it seems like it's a really good detector. But the problem is the amount of hydrogen ion is very, very high coming off of the column, and the amount of your analyte is very, very low. So this is the situation where you've got a very high background, and then you're trying to measure this little tiny signal on top of it. And we've talked about that's a really hard measurement. It's not a good measurement. So that was the problem with putting this method into practice. Okay, but in the 1970s, so it was actually 50 years ago, they figured out how to get around this. There's several ways. The most common is to use what's called a suppressor column. So what this is it's a second ion exchange column. So here is the stuff coming off the first column. Okay, here's my analyte that I'm trying to measure with its very small concentration. And here is the mobile phase. Okay, here I've got high concentration of hydrogen and chloride. So what I do now is I'm going to put an anion exchange column after the regular column. And I'll put this through that. So what happens is that chloride's going to get stuck onto the column. The hydroxide comes off and it will combine with hydrogen to make water, no conductivity. And then all I have left is that ion I'm trying to measure. So I've taken that very high background, the tiny signal, and I've lowered the background to 0, and now I can very easily measure that signal, get a nice big peak from that. And notice I didn't point it out, I forgot these concentrations up here in this table, part per million. Okay, so we're measuring very low concentrations of analyte when I do this. Okay, so that's the conductivity detector using what's called a suppressor column. And the next slide will just show you the same thing, just kind of in picture form. Whoops, sorry, I'm trying to get back to the pointer. All right, so here's the main column. Out comes, your little bit of ion with all that extra put in the suppressor column. And now we just get that signal I want to measure. One problem with the suppressor column is they have to be regenerated. This column gets filled up with all the ions that it's suppressing. So every 8 to 10 hours, you actually have to stop the experiment, run a high concentration of acid through to regenerate your column so you can use it again. Okay, so this method can be used to separate anions and cations like we saw. It's also useful to separate a lot of different organic and biochemicals. For example, amino acids, okay, are charged, so they can be separated. A lot of organic acids, which are seen here, can be separated as well. Okay, so ion chromatography. All right, next one, size exclusion chromatography. So the name tells size. So this is used for large molecular weights, big molecules like proteins and polymers. Now here, your separation is not interaction. There is no partitioning. It is actually sieving. We're separating things based on size. So our stationary phase is going to be a porous silica. And then you will have pore sizes. Okay, in that silica, you'll have small pores, anywhere from 40 to 2,500 angstroms. Remember, angstrom, 10 to the minus 10 meters. Okay, so there's two different ways to do this, or just different names. You don't need to know these names. So if the mobile phase is aqueous and the stationary phase is hydrophilic, okay, hydro, water, philic means to like. So these are polar compounds. Here, non-polar stationary phase, hydrophobic, water fearing, so they don't like water. These are non-polar. So they just give it a different name if you're separating polar versus non-polar. So one's called gel filtration, the other gel permeation. Okay, but the principle is the same. You're going to have this column, and it's basically a filter that's going to separate molecules according to size. So the big molecules will go through the column quickly, and the small molecules go much slower. Okay, their progress is retarded, it's slowed. So think of this kind of playground thing. And if we went over there and we took some small children with us and we said, oh, let's start on this side and we'll meet over here on this side. Well, of course, those small children, they're going to go up here and there's all these little places they can go into and explore, and they're going to spend a lot of time in there, and then eventually they'll come out over here. But, if you're bigger, like most of us, and maybe some of you guys are really big, I don't know, I haven't seen you, but most of us would have a hard time to get in there. We're too big. So we're just going to go around the outside and come out. Okay, same thing for this kind of chromatography. You've got the stationary phase with all these little holes, and the little molecules will get in there and go in through all the pores and then come out. Big molecules, they can't even get in, so they just go straight through the column. So you get this separation based on size. All right, so in size exclusion, the larger molecules come out first because they can't get into the pores. So they're not retained. And we call these first molecules that come out, we call that the exclusion limit. And we talk about it in terms of molecular weight. Okay, so these are the first molecules out, the biggest ones. And the exclusion limit is determined by how big those pore sizes are. Okay, then there will be some molecules that come out in between. These are the intermediate molecules. And then we have the smallest molecules. Okay, they go into all the pores. They're the most strongly retained. They will be the last ones that come out. Okay, and we call that the permeation limit. So this is what the chromatogram looks like out. So here, the very first peak you get out, that's the exclusion limit, the large molecules that are not retained. And then we have intermediate ones. And then the last ones to come out, that's the permeation limit. These are the small molecules. Those are the ones that are completely retained, go into all the pores, last out. Okay, so first out, big guys. Last out, small guys. Here's a couple of example separations. So notice, again, big molecules, things like proteins, or polymers, peptides, sugars. This one they've used to separate fatty acids. So notice the first one out, longest chain. Last one's out, shortest chains. This one was a polymer, first one out, the biggest one. And then down to the monomer, the single unit. Okay, so this kind of separation, you get short, well-defined separations. Everything comes out between those two limits, between the exclusion and the permeation. So normally you have pretty narrow bands and good sensitivity. You don't lose your solutes. You know, we've talked about sometimes the solute loves the column and it sticks on there, it won't come off. That doesn't happen in size exclusion because the solutes don't interact. It's just about size. And the column doesn't get deactivated from interactions because it's not interacting. A couple of disadvantages that everything comes out in a pretty short time. So, you know, we've talked about for the other methods, oh, if I need to improve K or improve N, what can I do? For this method, what can you do? Nothing. It is what it is. The other disadvantage is you have to have at least 10% difference between your sample sizes to separate things. So it can't, for instance, do isomers because most isomers have the same molecular weight. So you need a 10% difference between different solutes to separate them. Okay, so size exclusion. All right, lastly, it's either getting shorter, right? This is a newer form of chromatography. In fact, it's not even mentioned in your book, but it's become quite popular. So I put it in just to give you an idea of some of the current research. So this is a type of chromatography where you have something called an affinity ligand. So this is a ligand that is on the stationary phase, and it will bind to one and only one compound, okay? And it usually will bind to some kind of biological molecule, like a protein or an antibody or an enzyme. Okay, so it only is going to bind to one thing. And there's two stages. The first one is you're going to pour your sample into the column, and then you will get your target molecule stuck on to the column. And then the second stage is to change the mobile phase composition. Often you change pH to get it back off. So again, this is extremely specific. This will separate one and only one kind of molecule. And it's mostly used if they're doing work trying to isolate a specific molecule. This is a great way to do it. So this is a little bit hard to understand, but let me show you in a picture, much easier. So here is my column, and notice I've got my stationary phase, and then I've got this ligand on it. So this is the thing that's going to bind to one thing and only one thing. And now I have this mixture of proteins, okay? And this is the one I want, the target one. And all of these, this one, the target, is the only one that will bind to this. Okay, so I put them all in the column, and notice the target gets on there. It will bind to this affinity ligand, and everything else just comes through the column. All right, now I have them stuck on the column. So now I change the mobile phase, usually change pH, and off it comes. So I have now purified this protein from this mixture, okay? Affinity chromatography. Okay, so that is chapter 5. We have finished with chapter 5. So if you remember last week, I gave you quiz 5. I sent it to the WeChat. And so quiz 5 is for chapter 10 and 11. So you now need to do that quiz. You should do it on RAIN before next week, okay? We will not have class next week. We will be finished today. But next week, before the beginning of next week's class, you need to turn in this quiz. So you will have you'll have 30 minutes to do the quiz. So once you open it on RAIN, you must do it. It's not like a homework. You cannot go and look at it, then come back later. Okay? It's like a quiz. You open it, the time starts. Okay? And you have 30 minutes, but you already have a copy of this quiz. Okay, so you can prepare in advance and have all the answers ready. This quiz has no calculations, so you should easily be able to do it, especially if you have prepared well. Do note that the order that I sent you will not be the order in RAIN. Okay? RAIN will mix up the questions. So the order of the questions will be different. The order of the answers will be different. So you need to pay attention to what you're doing. Okay, but everyone should get a very high grade on this because I've given you the quiz in advance. Now, one thing, the answers have to be in the proper format or you will not receive full credit. Okay, so what do I mean by that? For this quiz, there are no calculations. So everything needs to be answered in the system. No pictures. If you give me a picture, you will lose credit. The matching must be given in this format. Okay? A number and a letter, like 1B, 2D. If you give me something different, like 3A, 1B, 4C, you will lose credit. Okay? I've asked all year, and some of you still want to do it your own way, and I want it this format. So this time, if you do not put it in the right format, you will not get full credit. I will give you the answers then for the quiz after it's due. Okay, so next week, next Friday, sometime during the day, you can look for the answers. And of course, I'll release the grades in the system. You can look in RAIN too. So as always, I will post the quiz answers in WeChat and in Baidu and in Dropbox. I'll also send them to RAIN. So several ways to access the problems. Okay, so that's quiz 5. Check the time. Yeah, let's go ahead and take another short break. And then we will come back and finish up. So we have to talk about the final exam. So you want to take a break and be fresh because you want to pay close attention to what I'm going to tell you about the final. Okay, so let's take another short break and then we'll come back there. Okay, before I go on, are there any questions about quiz 5? What you're doing there? Any questions? Okay, so final exam. So first off, the university has a policy that if you miss more than 5 classes, then I don't have to let you take the final exam. So I doubt that these students are watching because they have done nothing all year. So if you are watching and your student number is here, you may not take the final exam. There are a few others that I should not let you take it, but because you've done something, I'm going to let you if you want, although you probably won't pass. A lot of you are still missing attendance. And last week, the Zoom chat sort of messed up and didn't save half of the information. So if your student number is on this list, I'm going to give you one more chance to register your attendance. If your number is not here, then you have perfect attendance. You don't need to worry about this. So if your number is on this list, you need to send me a message with your name and student number. Okay, you can't just send me a message that says I'm here. You need to send me a message with your name and student number. If you are watching this by video and your student number is on this list, you need to send me an email saying that you have watched this video. So right now's your chance. If you don't do it, then you're not going to like your attendance grade, which is part of your final grade. So if you're here, you need to send me a message, name and student number. Okay, and again, I need your name and student number. Okay, now let's talk about the final exam. So the final exam will be January 7th. That's a Thursday, and it's going to be from 2 in the afternoon to 4:30. Normally the exams are 2 hours, but I'm actually going to give you an extra 30 minutes so that you will have enough time to deal with the uploading of pictures and that kind of thing. So the final exam will be on RAIN, and we'll use Zoom monitoring. So it will be like the quiz last night for me, yesterday afternoon for you guys. So the RAIN, again, you need to do that on your computer, not on your phone, and the Zoom monitoring needs to be on your phone. I need everyone to be signed in at least 20 minutes early. Because a lot of you didn't have your phones positioned right yesterday. A lot of you didn't turn them on. You didn't change your name. So we need to make sure everybody's ready to go so that you don't lose any time, exam time. Because the exam starts at exactly 2 and it ends at exactly 4:30. Sometimes on the quizzes, I've given you a little bit of extra time in case you've started late. For the exam, starts and ends exactly on time, no exceptions. So you have to be there early and ready to go. And it's okay if you're early and you're ready, then you just study a little bit more. It's not a problem, or read a book or something like that. Okay, so that's the time for the exam. Make sure that you have a calculator. Your phone and your computer are going to be busy with test things. So you need to have a calculator handy. All right, again, the websites for RAIN are here, and the Zoom code will be the same as for class, but I will send that to the WeChat. And again, you need to be signed in by 1:40 at the latest. All right, now we had lots of problems yesterday, so I'm going to go through this one more time. For the monitoring phone, you're going to connect your phone to Zoom. The camera needs to be on, the microphone off. This is what your phone needs to be showing me. A lot of you were showing me your face or just showing me just the area right here where your pen is. I need to see your computer screen and this area, and then a little bit of you, So that phone needs to be kind of behind you and off to the side. So you need to practice getting that angle. The angles of your face where I can't see your computer, those are not acceptable. Make sure your phone is fully charged. When you come into Zoom, you must change your name. I need your student number and your name, both of them. Now, the student number, if you want to just give me the last 3 digits, that's okay. You don't have to give me the long one, but you must have your student number and your name. There were a couple students yesterday that didn't change it. Their Zoom said iPhone. I don't know who you are, so that's not okay. Again, you can use that phone that's monitoring briefly to submit pictures. So make sure that that's the phone that's connected to your WeChat so that you can do that. So note, if you do not turn on your camera, which many of you did not yesterday, if you do not put your camera in the proper angle like this, if you do not change your Zoom name, then this may disqualify your test. Okay, what that means is your test will not count and you will have to take the test again next year. Okay, now nobody wants that, so you need to follow these directions. Many of you did great yesterday, but there were just as many who just did what you wanted, and that's not okay. You have to do it according to this system. All right, some other notes. Only the calculations should be submitted by pictures, nothing else. Okay. Note that the Zoom meeting will be recorded. So, those pictures you're putting up will be recorded and the university will keep those. Make sure that you keep your microphone off during the exam. If you turn on your microphone to talk to me, you are disturbing everybody that's there, the whole class. So keep your microphones off. If you need to talk to me, then either do it in the Zoom chat or use your WeChat. Okay, but do not disturb everyone else during the test. When you finish the test, leave the Zoom meeting. You don't need to stay. Once you've turned in your test, you can leave. You don't need to ask me. You don't need to tell me. Just leave. Taking your test on your phone is not allowed. Turning in your answers by email is not allowed. Now, many of you did both of these yesterday. And notice I have a star. They're not allowed without permission in advance from me. There's actually one student I know that cannot take the test on their computer. And there's one student that cannot upload pictures because of their internet situation. But those students have talked to me in advance and they have permission to do that. Now, the rest of you, you cannot just the day of the test say, oh, my computer's broken. I had 7 students yesterday tell me suddenly my computer is not working. That is not reasonable. I have taught Chinese classes where not one student has had a problem. So when suddenly there are 7 of you saying, my computer doesn't work, that is not believable. You guys cannot just do what you want. If there's a real reason why you cannot take the exam using these rules, you need to get a hold of me in advance. Not send me a message 2 minutes before the test and say, my computer's broken. Okay, so, and again, if you don't follow these rules, the university may not count your test. Okay, now let's talk about the actual exam itself. So the exam is comprehensive. That means it covers everything, okay? All 11 chapters. Roughly, there's 15 to 20% from chapters 1 to 3. There's 20 to 25 from 4 and 5, and then 25 to 30 from 6 and 8, and 9 and 11. Those are rough, but that's kind of roughly the breakdown of questions. The types of questions are similar to what you've seen on the quiz and homework. One reason we have had quizzes is so that you can become used to the kinds of questions that you will see on the final. The other is to force you to study so that now that we're reaching the final, you actually should know a lot of this material already. All right, so the actual breakdown for this test, there's going to be 50 points of multiple choice or true false. There will be matching and choose one. The choose one is just where you have 2 choices. And so there's 20 points of that. There's only 10 points of short answer. And then there will be 20 points of calculation, 3 problems. So that's a total of 42 questions. Now, that may sound like a lot, but it's actually fewer than normal. Okay, so I have shortened this test compared to a normal exam, and I am giving you more time. So you should have plenty of time if you study and know the material. Okay, and again, make sure you have a calculator, because your phone will be busy doing something else. All right, the exam is open book. You can use your notes, you can use PowerPoints. but you will not have time to look up every question. You know, there's 42 questions. You do not have time to go find the answer. Most of the questions you should be able to answer immediately, not go find it in your notes. If you're going to try to look up everything, you will not finish on time. If you actually know the material really, really well, you could finish the exam, finish everything, upload everything in less than an hour. But that means you really know the material. All right, again, it's open book. If you're consulting the internet to look at other websites, or you're talking to other people during the test, that's considered cheating, and I will give you a 0. I have no tolerance. I actually failed a student last year that I caught cheating on the exam. So just know I take it very seriously. So do not test me, because I will fail students for cheating. I do recommend that you try to have physical copies of the most important notes rather than trying to find all the different files on your computer, and also to have a copy of the equations. It'll just be much quicker that way. 2 of the most important things you can have are the answers to the quizzes and the answers to the homework problems, all of them. So I try to have those on paper if at all possible, because it will help you greatly. You also need some blank paper for the calculations. You need a calculator, and you need something to write with, a pen. You need to watch the time. As I said, I consider the time to be generous. If we were in person, the test would be longer and you would have 2 hours. So if you run out of time at the end, and there are still things that you didn't finish, you didn't upload your questions, you will not get credit. You cannot send me your questions by email because you did not manage your time. I actually recommend that you try to get those calculations done early in the test and get them uploaded so that you're not messing around. You know, if you wait till the last 5 minutes and then you run out of time, then that's your problem. So don't come back to me and say, I ran out of time. You need to handle this early. You have enough time, but you need to manage it well. Again, the instructions for calculations are the same. You're going to submit those by pictures. You have to have your student number. You have to show me your equations, your work. Make sure you have units if you need them. Watch your significant figures. Every other kind of question should be answered in the system, not by picture. So the short answer, the matching, answer them in the system according to the proper format. Again, matching should be in this format: number and letter, number and letter. And again, these are the ways that you can lose points on the calculation. So I talked about this earlier. I won't read through that again. I've mentioned these several times. All right, the equations that you need to know. So these equations you need to have handy. You know, I again recommend that you either print them or write them out and you have them right there so that you don't have to go find them. If we were live in person, you would have to have these memorized, but we're not. So you can actually write these. So make sure you have the LOD and LOQ equations. Make sure you have all the Beer's law equations, and make sure that you have the electrochemical equations. So you need to know these, and then you will also need the chromatography equations for calculations like the quiz from yesterday and the homework. Okay, specifically, what should you study for the test? First thing you should look at is the quizzes. The questions on the test are similar to the quizzes. And actually, I will say that if you actually totally understand the quizzes, that's 80% of the final. Now, what I think is totally understand and what you think is probably different, and I'll talk about that, but quizzes are extremely important. Make sure you've studied the quizzes on all the quizzes. All right, next thing, make sure you look at the homework chapters. You know, at the end of every chapter, there were homework problems. A few of them you gave me, but most you didn't. So make sure you've looked at all of the homework problems at the end of every chapter. I have given you the answers to these, so that shouldn't be a problem. For the calculations, make sure you know how to do these calculations, okay? So you may see other calculations like these on the exam. So make sure you understand these calculations especially. Okay, now I have already given you the answers to the quizzes and the homework, but I'm actually going to send everything again. I'm going to put all the homework answers together. There'll be the original document, and then all the ones you've turned in, I'm going to make one document for you. I'm going to take all the quiz answers and make one document, and I'm going to resend that. So I can send the homework after today's class, but the quizzes we have to wait until after next week's chapter 5. Okay, but I will resend this in case you've lost that, because again, this is the key items that you need to study for the exam. If you know all the homework questions in the book, then you should get 100 on the test. Okay? I'm not going to be asking questions that aren't in the homework. All right, so when I say, you know, make sure that you have studied the quizzes. Okay, someone asked about the recorded videos. The recorded videos are on Dropbox and on Baidu. They were sent to WeChat, but you probably can't get them anymore, so you'll have to use one of those other sites. Okay, I made a statement that if you actually understand the quiz material, that's 80% of the test. So what do I mean by that? Well, here are some old quiz questions. So let me give you some examples. So this question, the ability to distinguish between small differences in analyte concentration, selectivity or sensitivity. This is a choose one. All right, now you might say, okay, I'll just memorize this question. But when I say you should really understand that, you should realize there are different ways I could ask this question. I could say sensitivity is A, you know, the ability to distinguish between small differences. B, you know, the concentration range where something's linear, you know. I could make it multiple choice. I could make it true, false. I could be asking about selectivity instead of sensitivity. So when I'm saying make sure you understand everything, realize that this question can be asked many different ways. It can be true, false, multiple choice. I could make matching. Here's definitions, here's terms. And then make sure you understand every term that's listed, not just the one I asked about. You know, from my point of view, this question's not just sensitivity. You should also know what selectivity is. This one, an analyte that dissociates, is a type of what kind of deviation. Okay, this one was chemical. But you should also know what are examples of instrumental deviations. What is an example of real deviations? Solar deviations don't exist. I made that up, so you don't have to know that. But you know, make sure you look at each choice and understand that. These two questions are both asking about graphite furnace compared to flame. So, you know, here's two things that you have to know about LOD and matrix interferences. But we talked about other things, so make sure you know all the comparisons for flame versus graphite furnace and how they compare. This one, which form of mass transport is movement due to electrostatic attraction between electrode and ions? Okay, that's migration. But you should also know what is convection, what is diffusion. Okay, adsorption has nothing to do with mass transport. So when I say, you know, 80%, that means looking at all the concepts, realizing that things can be asked different ways, and there's, you know, other information there that you should know about. Here's an example of a matching. Okay, and again, this is how you should answer this. But notice this one, there's two terms I didn't use. You should know what is polarization, what is activity. Again, this could be a multiple choice. You know, junction potential is A, this one, B, C. So different ways to ask the same information. Give two sources that are used in AAS. So this one's a short answer, but that could be a multiple choice. It could be a choose one. It could be a matching. Here's a bunch of sources. Here's the type of method. Which one would we use? Okay, so when I say study the quizzes, you have to think beyond that one question. You have to think of other kinds of things that will be encompassed in that. Okay, so that's studying for the test. All right, so the materials, again, there's the Baidu site that has everything. Has the videos, the PowerPoints, the quiz answers, the homework answers. There's some PowerPoints where I've, like this PowerPoint that I'm doing now about the final will be there. So that's one place that has everything. Another place that has everything is Dropbox. If you are in China, you probably cannot access Dropbox. If you're outside of China and you want to access Dropbox, you need to send me an email, and then you'll have to create a Dropbox account. It's free, but you'll need to do that if you want to use Dropbox. Right now, there's only 2 people that are using that. I have sent all of this to WeChat, but WeChat's hard because, you know, you maybe cleared out your memory or maybe the videos don't work anymore. I will resend the homework answers and the quiz answers so that you will have those fairly fresh. I will also send the homework answers and the quiz answers to Rain so that you can access them there. I cannot upload videos to Rain. So if you need the videos or you need PowerPoints, you're going to need to go to Baidu or to Dropbox. Okay, that's where you can find stuff. All right, if you have questions, I'll have 3 different times. We'll have to do it by Zoom. So it will be our normal meeting code. And so next, these are all China times. So next Tuesday, not next Tuesday morning, the week after next, before the test. So Tuesday morning and Wednesday afternoon and Thursday morning. Now, note, I have 2 other classes that I teach. And so there may be other students, there may be Chinese students, because I will give them the same times. And also note that help session for me means you have a question. If you want to just come and say, so teacher, what's on the test? Teacher, what should I study? Okay, I've already answered what I'm going to tell you. So don't come if you just are going to ask me that. If you want to say, I don't understand this, then I will help you. But if you want me to just tell you more information, then don't come. Okay, don't waste your time with that. And you'll have to turn on your camera and you'll have to turn on your microphone and talk to me if you have questions. You can always use the WeChat group, and you can always use my email to get a hold of me. You know, those, it's not always instant if, you know, because I'm in a very different time zone than you guys. Right now it's almost 7:30 at night here for me, so sometimes you may have to wait. Okay, so our exam, January 7th, 2 to 4:30 China time, be signed in by 1:40. Okay, so we are actually finished. I think that's it. Let me double check. Yep. All right, so we are actually finished. So we will not have class next week because I finished, gone a little bit over tonight. But so extra 15, 20 minutes and I'll save you a class. Okay, so no more class. The next time I should see you would be for the exam unless you have questions. I will post the answers to quiz 4, and I'll post this PowerPoint at some point tonight. I'll also post the video as always. Sometimes that takes several hours to get it all uploaded. So any questions?
Teacher, actually I have a question about the attendance.
Mm-hmm.
You just show up. You just show on the screen. You just show that I need to register for today. Does that mean that the other days when I register, you don't receive it?
If I did not show your number, that means that you have full credit for attendance.
The teacher, you just show my number, but I never miss your class.
Well, then you haven't registered your attendance sometimes.
Every time I register, teacher, every time.
Well, you haven't, so.
Okay.
Other questions?
Hello, teacher.
Mm-hmm.
Actually, I prefer to use a laptop in time of giving exam. Okay. So, but last day I tried to access from my laptop, but I couldn't. So instead of that, I heard some student talk to you. He also facing like the same problem.
Mm-hmm.
So that time I used from my cell phone. So today you mentioned we can't give exam from our cell phone if we can't enter from our PC. So what can actually we can get the solution?
Have you ever used your PC
Yeah,
for anything?
maybe second quiz, maybe second quiz. But number third and number fourth, I can't access from my PC.
So if you truly can't access it, then you can use your phone, but you need to send me a message telling me the situation.
Okay, thank you. But I will try to.
Yeah, you need to
from
try
my
the
PC.
laptop first.
Yeah. Thank you.
You know, if I get a few students that really can't, then probably it will be okay. But if I get a lot, then the university's going to come back to me and say, no, this is a problem.
All right.
Okay, any other questions?
Yes, last week, I would like to ask about the practice quiz. Is it okay if you can send it so that we can just try to, use the system? Because I remember the last time my phone and computer almost failed me, so I would like to, just maybe practice with it. Kindly asking if you can send the practice.
I will send the practice quiz again. So if you want to practice it, if you're going to practice it on your phone, there's not much use. But if you want to practice on your computer, I will send the practice quiz again for those that want to practice.
All right, thank you.
On their computers. And that way, if you have problems, then you can talk to me ahead of time. But if you just wait till that day, then we might have problems. Anything else?
Yes, teacher, I have a question.
Go ahead.
So like yesterday during the test, during the quiz, you have talked about this thing about the student talking during the quiz time, and I yesterday I actually get distracted about their sound, what they're talking about, and take my attention to hear what they say during my quiz. So how can you make sure it will not happen in the final exam?
I have the ability to actually lock out everybody's microphone. So I'm going to do that for the final exam so that people will be unable to turn on their microphones.
Okay, that would be nice. The other is also about you showed some student ID here. So, and I didn't pay much attention to look. Maybe my student number is there.
Well, then just send me your name now, and if it's there, I'll record it. If it's not, you're good.
Okay. That's all. Thanks.
Okay. Anything else?
Hello, ma'am. My name is on the list, so what should I do about that?
I told you what to do. Send me your name and student number, right? And I'll give you credit for last time.
Oh, I just sent in the comment section.
Okay, then you're fine.
Thank you.
Anything else? Okay, I know this has not been an easy semester for you. I know this is a difficult way to learn. It's a difficult way to teach. I'm sorry about that. But that's the situation we're in. So you just have to do your best. And I hope that you will all do well on the exam. If we ever all get back to China and you see me around campus, you can say hi to me. But I'm hoping not to have you again as students. Hope you all do well on the test. And we'll see you in a couple weeks for the final. Okay, so we'll stop there if there's no other questions.